Hello, welcome to Engineering Design in Omniverse. All right, we've got a few people here already. Today I've got a good one. I've been working all week on getting this car rigged up and ready for simulation. So if you remember from before, we've designed a really basic remote control car in CAD, and it's just, we've got the main template, we've got the suspension modeled just with lines and points. And the reason that we've done it that way is I built it up as a template so that anyone with one of these cars, so if you have some other remote control car, you can measure it with a ruler. You can put your numbers into this CAD template that I've written, and it will kind of morph to fit your suspension geometry. And then you can import that into Omniverse. So if you have those measurements and if you have some basic weight measurements, you should be able to simulate your car pretty well in Omniverse and use it as a robot. So let's see here. Let me show you my screen. And I just want to show you my results so far from this week's work, where we're at. Here we go. So far, it doesn't really look any different from last week, right? The same parts are there because we were done with the CAD last week. But if you've seen me drive the Jet Racer before, you might notice this is a little different. I've got my gamepad right here. So there's my throttle, there's my reverse. And here we are driving it around. And what you might notice is it's a little faster. Yeah, a lot faster. Let me see if I can get this thing going. Let me switch to my other view. Before, I could drive with the Jet Racer, I got it go so it would go maybe 4 miles an hour. I don't know, not very fast. This one goes 30. Yeah, donuts requested. We're doing donuts right now. And honestly, I'm driving this to do donuts. It's really wild. I drive this I did off-road racing. And in off-road racing, you need to kind of drift around the corners. And the way you do that in those cars is you actually just mash the brakes before the corner, which lifts up your rear tires, and then you mash the accelerator, which gets your rear tires spinning, and then you can throw that rear end around the corner and drift. If you look at this, if I'm driving, just turning, it doesn't break loose. Oh, I went off of the ground plane there. But if I mash the brakes and then hit it, I'm doing donuts. So the physics are really good. That's actually how I would do it in a real car. So, oh yeah, the suspension is working. So Zia says the rear tires tilt. Yeah, let's go a little slower so you can see better. I'm going forward, and you can see those tires are tilting, and the suspension is moving. I'm going to make it extreme by turning hard. Oh yeah, the suspension is actually working, and this is actually the lowered Traxxas / suspension geometry, at least relative, pretty close. Yeah, it's pretty cool. So yeah, this is not a game. This is a simulation. This is not. You can do simulations with the physics car template, but those tires just move up and down, and with it just has a sprung mass in the middle. I just put together joints and rigid bodies and built a working car from primitives, so just from scratch. And it's a template so that once I can release it, you all will be able to open up Onshape, measure whatever remote control car you have, plug those numbers in, and boom, you're simulating your own remote control car right in Omniverse. So really, I'm really happy with how this is coming together. Let's talk about, I don't know if you remember from last week, but last week it was when we ended, I believe it was still exploding and flying off into space and all this nasty stuff. So let's take a step back. Let's import from Onshape, and let's go through some of these steps to get where we were at now. So let's just create a new stage. And please, if you have questions as we go, please ask questions. So let's create a ground plane. By the way, just to show you the way I've done this, I've got just an environment here. This could be an environment with a track, whatever you build. And the way I'm doing this is you just insert this sublayer, this car sublayer, and look, it's put all of the car and all of the physics settings you need into the scene like a macro. So just to show you, if I run now, does it put the camera? It even puts the follow cam in. So that brought all of that work in one shot by inserting that that sublayer. And so if you build a track, so I've set this up in such a way that you can build a track first and then import the car and the physics settings into the track all at once. But let's remove that sublayer and kind of start to build the basics of this car. So we're going to start by importing from Onshape. Gotta authenticate. There we go. Here it is. Import that. Great. So now the car is imported, but if we run, if you remember, we get all these errors. And so we're going to be kind of go over a few of these things again. But if you remember, the first step, a lot of those errors we're seeing is because of the articulations. Let's see here. What do we got here? Oh, when I deleted that layer, it didn't do everything. Here we go. So if we go right here to full car, I believe, you'll see it has an articulation root. And we want to delete that and redo that on the chassis because it's our center of our articulation. And you can think of it as, if you have a robot, I think of it as like arms, right? You have got the body of the robot and you have arms and limbs that come off of it. And you want whatever that body is to be your articulation root. In this case, the chassis, and then the suspension extends off from there. So we'll go to add physics, articulation root, and then we're back to there. So let's run it again. Make sure it all still works. Great. And so here are all of our joints. We're going to just find these 4 upper arm joints, and we're going to exclude them from the articulation. Oh, you can only do them one at a time. Excuse me. Exclude from articulation. Right there. And now if we find these other 2 upper ones, here we go, these 2. Exclude. Now, when we run it, we're still getting some errors, but fewer. Excuse me, I have a little bit of a cough. I'm going to grab a cough drop. came prepared. Okay, so we still have some loops in our articulations because of these shocks. So now what we'll do is we'll go to these chassis underscore shock. Here we go. And we're going to exclude those. So what I'm looking for, if you look at these articulations, they should just extend out. If you look at these arms, there's a loop here. So the chassis, this got a chassis mount, loops out and comes back to the chassis. No good. Here with this, there's a loop because it goes, the suspension's mounted to the chassis at the top. That loops around through the bottom arm and then through this shock. So we got to just pick some joint in those loops and break them up. And I'm actually wondering if I did that bottom one instead of the top one, would that break up both loops in one go? Would there be a loop from here? I think there would still be a loop. Yeah, but kind of in a figure eight, maybe. Excuse me. I don't know. This is going to be fine for now. I'll play with that later more this week. So let's exclude those from the articulation. And let's do the let's do the front now. Excuse me. Just have that little itch in my throat, you know? All right. Got chassis shock, arm shock, arm shock, arm shock. Oh, that's the wrong label. So there we go. But that's the one we want to exclude. And that one. Now let's run it again. Yeah, so all those errors are gone now because we've found some joint in each of those loops and broken it up. What we can do during the simulation is we can also now hold shift. We can pull on things. This is where we were last week, isn't it? Which we could drag this thing on the ground. Oh dear. There. One minute. What did I do wrong? I wonder if I did kinematic enabled instead of I did the wrong thing there. Let's try it again. Where is that? The steering knuckle? Shouldn't be a mistake. Just gonna undo a bunch. I really don't know what I did. So I'm just gonna go back and start over again. That's weird. I must have done kinematic enabled on some joints or something without realizing it. If you do kinematic enabled on a part, then it kind of freezes up. Okay, let's run this again. Oh. It's just, huh. Well, we get to debug that. Just taking a look at the physics here. Oh, there's no physics on it. Like if we select the steering knuckle, you'll notice there's a rigid body on it. These, do they have a? We don't. So I'm not sure why that happened. If I did something in my CAD, but for the sake of just showing you the cool stuff, I'm just going to open up my good scene here. I'll just go over some of what I did. All right. Here's back to this working one. Just lift it up in the air. I'll just show you kind of how I did this. So first I lifted it up in the air. And then the next step was to get all those joints working. So I went through the articulations and I fixed that problem. And then one of the hardest parts with the rigging that I found is getting these shocks to lift the car correctly. And I think the key there is to trust the solver a little bit. When you enable the kinematic mode and when you turn off gravity, which are two things I do as I'm building and debugging these joints, it kind of messes with the physics. And then when you turn those all back on, the physics work a little better. So if you try to tune the shocks with some of those funny settings, it's not going to be very good. But if you just put in the spring rates that you have, like that you really have or close to them, that's going to get you further down the road. And let me explain what I mean by that. Let me grab my car. So I know how much this car weighs. And so I can measure how much this wheel moves. And it's a pretty close estimate to how much this shock plunges as the wheel moves. And so if I go, this is my full droop. If I just set the car down on its own weight and see how much the tire moves, then I can use that as an estimate for how much this spring has compressed. And I know how much weight that's lifting. 1/4 of the weight of the car. And so that distance, a fourth of the weight of the car divided by that distance is the spring rate of these springs. And if you know your units here, we're in centimeters. Our weight units in Isaac Zimmer kilograms. And so you can just, that's your spring rate. So just throw that number in. That's what I've done. So if you go to any of these joints, let's see, here we go. Shock front right. You'll see that, there you go. The stiffness, I just put 2 in there. That's 2 kilograms per centimeter. That's how strong those springs are. Great questions. Is there a way to measure spring compression directly without the vehicle? Sure. You could take a spring off and put some weight onto it and measure how far how far the spring flexes. Good to go. And typically if you buy a spring, you probably buy it with the spring rate. It's just probably a specification that it gives you. Okay, great question. Did you consider the center of gravity from all the parts? Or did you just put in the weight and assume that the center of gravity is roughly at the center of each part? The center of gravity in Omniverse will be at the center of gravity, the center of the centroid of the mesh. Let me show you what I mean. Another really cool tip here, if we go to Window, Simulation, Debug, we get this really handy physics debug window. And you can check this simulation debug visualization, check that on. And then if we say, I think it's body axes and step. No. There we go. Body mass axes. And then let's just run it here. This shows us the bounding boxes kind of for each. Oh, where are you? These objects. And you can see that you can kind of see where they are. This is one way I would debug any problems, is if some of my center of masses seem weird, or like especially with the wheels, for example, if for some reason the center of mass was off to the side, the wheels would wobble while they roll. So this kind of helps you just get an idea of what those look like. Just keep in mind that they're typically one step, kind of just a little bit off. They're just one step behind. So it gives you an idea. There we go. So let me take a drink here. What else did we do? Okay, so let me explain how the springs work in Omniverse. The way that you apply a spring to a joint, what you do is you apply limits to that joint that it should not, so some limits that it should not exceed. And then if the joint exceeds those limits, well, first of all, if you have 0 for all of these advanced properties, that'll just be a hard limit. It'll hit that limit, it will bounce off of it. If you apply stiffness and damping to those joints, then when it hits that limit, that's when it will start to kind of figure out, and use the spring and the damping forces. And so as far as this car goes, what you want to do is set it down and figure out your ride height. And you lift it up and you figure out, well, okay, how far did this wheel droop from ride height to full droop? And this value right here, that's where you want to set the limit. And then the limit, you actually want it to be in the opposite direction so that no matter what, this limit is exceeded. No matter where, you always want this to be exceeded. You always want to try to push it down to this full droop position that the real car has. Okay? And that's what we've done here. I measure that. It's what is it? 1 centimeter below ride height. And so my lower limit is at 1 centimeter. And then my other limit is at 5. I put it at 5 centimeters below ride height. It's way down here. And so it's only supposed to be allowed to rest in this position, which it can never reach. Okay? Oh, sure. Let me demo that droop again. Zia asked. Let me see here. So here you can see the wheel articulating. And if I set this car down, it goes to about here. It's 1 centimeter. This is kind of rough. And so what you want to do is you want to, this lower height, 1 centimeter down, that's your one limit. And then way down here at 5 centimeters, I'm saying it's okay if you're from here to down here, which it can never reach. It can never reach that. That's just guaranteeing that as soon as it hits, it's just trying to always push it. Is that right? Yeah, it's always trying to push it down to here. It's a little confusing. I'm not going to lie. I had a hard time with this. And so I'm going to show you how I debug that. All right? Not to worry. But just keep in mind that, so these are not actual limits on these shocks. They're not hard limits. It's just telling me where it should apply the spring, or when it should apply the spring. Now, in order for stability, I do need hard limits, because what will happen is if you don't have hard limits, then that suspension can get flipped around. And so the way I did that, so I applied the spring rates and spring and damping to each of the shocks. And you can just pick a joint, and I picked these inner lower arm joints. Let's just pick one of these. Here we go. And I applied hard limits to those joints. And for those hard limits, oh, you need to see my screen again. Thank you. Let's see. There we go. Here's my screen. So I picked these lower arm to the chassis joints, and I've applied, you can see there's this red arc. That shows that I have a hard limit. I have a limit applied to those joints as well. And those are my hard limits. And for those, I just played with the suspension while it was in zero gravity and this chassis was kind of in kinematic mode. And I'll show you that in here in a minute. I just played with those joints until, with those limits, until the suspension wouldn't kind of get inverted or kind of get messed up. Well, let's show you some of that. Right now, we're just physics on, right? Let's go to the physics scene, and let's set the gravity to 0. Now when we simulate, we're just seeing, let's catch it here. I think it's the, oh dear. Let's catch it. I can't catch it. The what you're seeing there is that the shocks extending the wheels kind of added some momentum to the system and got it moving. So let's stop that right now. If we go to the chassis, and if we select kinematic enabled and run it, so now the chassis is stuck. So now we can grab these joints. Oh, see how that's inverting? That's exactly what I want to make sure it doesn't happen. It doesn't happen too often. I can do it. But you just want to fiddle with these joints until it doesn't happen while you're doing your simulation. Because if I'm just pushing down on the shock, it's not inverting it. I have to like pull it in on the wheel kind of hard. That's pulling really hard. And same thing in the front. I'll just play with those limits. See, I'm hitting those. See, I'm hitting those hard limits right now. It's not the shock that's doing that. It's that lower arm joint. And my mechanism is not inverting. Let's see. If I pull in, can I? Oh, what you're seeing there is the steering joint in the front. Yeah, so that one won't invert. And if I fully compress it, you can see it tries to extend. There you go. So you can see that the limits were working pretty well. You're just looking for direction here. You can't really trust the values when you're in 0G and kinematic mode because the masses aren't doing anything. It's just, and the kinematic mode seems to kind of throw things off a bit. So really with kinematic mode enabled and in 0G, you're just looking at these directions to say, okay, is it pushing the right direction? Let's see here. So let's go back to the chassis and turn off kinematic mode. Let's go back to our physics scene. 980 centimeters per second squared. Let's turn that back on. And really good. Gives a pretty good bounce, doesn't it? Just because I lifted it up way in the air. Just so I could see well. Let's do that. That's more like it. And you can see from that setting, let me just look at it from the side. If we run this, it's sitting right. Remember, this came in at ride height from CAD, right? I designed it at ride height. So it should stay about this same ride height once it's running. And you can see it gives a little bounce and stays at right height. Let me just stop it. I don't know why it rolls off there. I wonder if I have a joint active or something. I must have, let's look at those, these joints and see if they're running. Oh, that's the steering. So the steering's got some values. Upright wheel. Just looking at, yeah, I've got some position and velocity here. Interestingly, I'm not seeing the joint drive on those. Let's see if I can see them on the knuckle to the wheel. Oh. Let's make sure everything's still working like it should. Yep. All right. I think once if I just disconnect from the joint controller, I think it leaves some speeds on those wheels and stuff, so it's driving forward a little bit. Because what I do with this gamepad is when I hit the throttle button, I'm setting those 4 wheel joints and I'm giving them a speed so that it, basically driving those motors. And for the steering, I'm actually setting just the steering angle on each wheel. Okay, but the real magic, that's kind of not, most of that you've seen before in these live streams. But let's just go through and do this now. Let's delete this physics scene. Now, if we run it, you see how much it changed all of a sudden? How jittery it is? Let's run it now. Okay, and it got really unstable, right? I can't even drive forward now. Okay, off it goes. So let me show you how I fixed that. And actually, one thing that's already helping is I have a rubber material that I made with, and these are the dynamic and static coefficients of rubber and the coefficient of restitution, which is, how bouncy it is, of like a tire on concrete. So I set these parameters similar to a real tire and similar to a real tire. And keep in mind that with both friction and coefficient of restitution, you can change this as a setting, but usually the physics engine will take, just a quick explanation. Like static friction is not actually a property of rubber. It's something you measure of between rubber and some other material. So it's kind of this combined thing. So in the real, in real engineering, you would do tests and you would test the rubber on different materials. And if you were going to calculate something, you would actually use that coefficient for that combination of materials. The way that these physics engines handle that is you set a coefficient of friction for the material, and then when it takes both materials, it will average those. So if you have a relatively sticky material, it'll have a high coefficient of friction. If you have a relatively slick material, it'll have a low coefficient of friction. And then the engine will average those at runtime. And that gives you an approximately what you would actually get without having to enter the coefficient of friction for every material combination out there, which would be unsustainable. So that's how they do it. And the same thing applies to restitution. That's the bounciness. That's not actually a property of any given material. It's also a property of a combination of materials. So what I've done here is I'm only care about the bouncing and the friction between the tires and the road. And so I've just actually picked my my actual values of that combination, and I've entered those as a material, and I've applied that material to both the ground and to the tires. And that way it averages to be the exact number I want. There you go. That's how I handle that. There are other ways. If I had more materials that might make contact, what you can do is in the solver, you can set, instead of averaging, you can set it to be the higher or the lower, or there's some options there. And so let's say I was going to drive on different materials with this car. What I would probably do is set the coefficient of the rubber to be like really, really low, so low it would never actually be that value. And then for each material that I wanted to contact with, I would set the appropriate coefficient of friction and restitution. And then in my solver settings, I would change the settings to be the higher of the two values instead of the average of the two values. And then as I drove across different materials, the coefficients of friction and restitution would be correct. So, but in this case, we're only doing the one combination, and so this little bit simpler way does the job. And then let's see here. Let's undo here until we get our physics scene back. All right, there's our physics scene. Let's just go through some settings here. The default setting is the TGS solver. The TGS solver, it does more friction calculations. And it's also it's run on the GPU. So it turns out with these solvers, they do some things on the GPU and some things on the CPU if you allow them to. And there are certain calculations that work best on the GPU. In particular, if we're doing collisions of a large number of objects, or if we're doing soft bodies like a fabric. We're not doing either of those. And so for us, turning off the GPU dynamics simplified the solver's work and stabilized it. And then changing from TGS to PGS solver really helped a lot. And then I just played around with different collision systems and broad face types until one seemed to work well. And I could definitely probably talk to someone about that and do better. I read through the documentation, and I don't understand those settings very well, but I just played with them until they were working a little better. Another one that really helped out a lot, the minimum position iteration count and minimum velocity iteration count were at 1 and 0 respectively. I changed them to 10 and 5, and I played with these numbers until that made a huge difference. Just requiring it to always do a few iterations on some of those calculations seemed to really help. And then I played with the time steps per second, and I've been told that can really help improve the accuracy of your calculations. That wasn't helping me out. And so I have a hunch that once I meet with, I'll try to meet with someone who really knows this solver better than I do, and we'll see what we can do. And I just want to point out right now how big of a flex this is, because the fact that we're not only simulating a car, it's a tiny remote control car with parts that weigh like 5 grams. This thing is tiny. It is so small. And for most solvers, I don't know. I haven't tested a lot of solvers, so I shouldn't comment on most solvers, but it's just really a recipe for major round-off error to have such lightweight parts and such small parts. So the fact that this works at all, I find amazing. So of course, we run into some stability problems. We're simulating tiny parts that are very lightweight, and that is, that's often a kind of a, that's tough. That's tough. Which reminds me, one of the first things you should do when you do these when you run these simulations, is set weights for your parts. So the default weights, I don't know what they are, but they don't work very well. They're different parts depending on their volume will be widely different masses, and the solver will be pretty unstable if you just let the system do its default weights. You want to apply weights that are, and if you're not sure what to do, if you don't have weights yet, it's okay. Just apply a weight of 1 kilogram to everything, and you'll find that adds a lot of stability to your simulation. Then go back later and add your actual, your real weights. And in this case, all I had the chassis weighs 3 kilograms. The main car weighs 3 kilograms. The wheels weigh 120 grams. The uprights weigh like 30 grams. Then all the other parts are like 5 to 12 grams. They're really small, really light. And so I did the actual masses of the chassis and the wheels and the uprights. And then for everything else, I did like 10 grams. Accurate enough for what we're doing. Okay. You don't have to split hairs with this stuff. Okay. Back to the solver settings. And then if you go into the advanced section, there's this really good stuff. Enable stabilization. So this enables an additional stabilization pass in the solver. So it's going to take, we're going to take a hit on performance of the solver, but totally for this one, worth it. Yeah, this one too. Improved determinism at the expense of performance. Check. And then I think this was on by default. So, but those two stabilization effects really helped a lot. So if you're doing something like this, if you're not running into performance problems with your solver, if it's keeping up, turn those on. What else? Yeah, that's it. Those are the main settings that I tweaked. Of course, it takes a lot longer to figure that out when you're just playing with everything. But yeah, there we go. Now it's rolling forward. Let's go back. There. I could just do this all day. I'm trying to think of what else. You know what I wanted to show you is the difference between articulations and not articulations. So let's go to this camera. So let's just drive around. I'm going to go kind of low speed. You see we're a little twitchy, and I want to work on that. I wish it was better. But as far as what we're doing, trying to train a car to drive itself at low speeds, I think it's good enough. Because really we want the car to learn that if you steer this way, you go that way, right? If you steer this way, you go that way. More throttle goes faster, less throttle goes slower, right? Those are the core things that we need to teach this AI. And I think the performance is good enough for now. And even with if we wanted to do drifting, I think it's probably good enough for that, because I think it could even teach it those controls. That said, yeah, I definitely want to work on this a little more. Still a little twitchy, isn't it? But I do want you to point out which joints are a little twitchy. They're the ones that we've excluded from the articulation. Look at the joints that are part of the articulation. How do they look? They look really good. So it's just, and maybe I could work with, I got to learn more about this, because I'm noticing that those are the joints that are twitchy because they've been excluded. And so it makes me wonder things like, would excluding certain joints work better for the simulation? Is there something I can do with the solver to improve those settings, to make those a little less twitchy, that sort of thing. But I just want to show you the difference that articulations make. So I'm going to go to the chassis, the articulation root, and I'm going to disable the articulation. Oh, great question. How can we tell what kinds of joints we have? If you add an articulation root, it automatically makes them all articulations. It does that automatically for you. It detects that you've done that, and it figures it out. Keeping in mind that we can't have loops. So on this screen, for example, look at the arms. This one's to the chassis, which is our articulation root. It comes out to the wheel and then loops back to the chassis. That is a loop, and it cannot do that as an articulation. And it has errors if we try to do that. And let me reproduce that real quick. If I come to this joint, let me show you. Here we go. Now we want chassis, A-arm, rear, upper, right. So I have this exclude from articulation. I'm going to uncheck that and run the simulation. And it can't handle it because there's that loop. And so it just randomly picks a joint and just doesn't calculate that joint for us. Just so the solver won't crash, I think. So we strategically pick the joint we want to exclude and select, where did you go? Here we go, exclude from articulation. And we're saying just use a more classical video game joint for that one. But for the rest, we'll do articulations. And you see that joint is twitchy, but these articulation joints really are not. These ones are twitching because this one's making them twitch, right? But it's not moving relative to the upright. So that's how you tell what kind of joint you have. Let's go back to this articulation root to the chassis. And let's turn off articulation. Oh, by the way, look at this. We have all these other settings too. There are a lot of solver settings we can play with. And I think there are even more in the physics settings. If you go to File Properties, I've just, you go to Edit Preferences. And I think Physics. Yeah, even more settings. And so there are really a lot of settings we can play with here. And I just played with them enough to get the simulation working relatively a little, so it's a little stable. But I'm pretty confident we could do a lot more stabilization here. That said, back we go to the chassis. Just want to show you. I'm going to turn off the articulation solver. So I uncheck articulation enabled. And now it's going to pretend it's just going to use standard video game joints for these. Okay, first of all, my spring rates are way off. I don't know. Look at those. Look how sloppy those joints are. Look at, I mean, for heaven's sake. It definitely video game. It'd be okay for basic ragdoll animations of a video game, but we couldn't drive a car with that. There's no way. So turn those articulations back on. Look at that difference. We can drive around again. There you go. Yeah, so I'd like to hear questions. I'd like to hear, I can talk to you a little bit about next week. So what I'm going to do this next week is I'm going to go ahead and add all the sensors to this car. So I'm going to add a stereo sensor and a LiDAR to it. The same ones that they have, the standard F1Tenth sensors. And that'll add some mass up high. That'll change the center of mass a fair amount, and it will give us some sensors to work with. And then, so next week, what we'll do is we'll show off those new sensors and show what that looks like. And we've got Michael Gussert from the Isaacson team has been working on some tracks for us. And he has come up with this really, it's like an elegantly simple way of building tracks with 10th scale cones. So the idea here is I've got these orange cones I bought. Here, let me grab one. Be right back. They're right here. I just got these at the sporting goods store. Just some orange cones. They're, not too big. And so we're going to build some tracks out of cones. And Gus, we call him Gus, has come up with this really elegantly simple way of building tracks in Omniverse out of cones like this. And I think it's just good enough for us that we can build a few tracks to train with. But I bet you all could take what he's done and expand it to be to let us build all sorts of tracks. So we're going to have him on next Thursday. We'll talk about these sensors. And great question. Will we use SimReady cones? Yeah, I think so. Why not, right? I definitely would. Remember that with that solver, well, there are no joints, and so those won't be articulations. They'll use the video game solver, but I think that'll be great. It'll be kind of fun too, because if we run into the cones, they'll bounce off and fly away. And I think it'll be really fun. So yeah, so we're going to have Gus on next week. We'll talk about sensors. And so what we should be able to do next week is take this car and drive it around a track by hand with a gamepad. And I can't wait. And until next week, have a good one.